Okay, so I had to break the video because YouTube doesn't like things. It takes too long to upload stuff that are more than 15 minutes long, and they have restrictions and stuff. Someone asked, how long is a light year? Okay, a light year is not a period of time. A light year is a measure of distance. Okay, think about a car driving down the road going 70 miles an hour. Okay, how far do you go in an hour? 70 miles. How far do you go in 2 hours? 140 miles. How far do you go in 3 hours? 210 miles. Okay. So if you wanted to say, if when I say that Bowling Green is an hour and a half from Louisville, I'm measuring, that's a distance measurement that I give in terms of time. The same thing that goes, so Bowling Green is 1.5 car hours from Louisville, right? Same thing with light years. A light year is a measure of distance. Okay, it tells you how far away something is. So I say Sirius is 8 light years away. I mean that its distance is such that light takes 8 minutes to get to Earth. Sorry, 8 years to get to Earth. The sun, by contrast, is 8 light minutes from Earth. It takes the light from the sun 8 minutes to get to Earth. So if you were Dumbledore and you could magic away this, everything in the sky, like so right now I just cast a spell, and the sun ceases to exist, and Sirius ceases to exist, and say Rigel ceases to exist, and Deneb ceases to exist. In 8 minutes, nothing would change at first. And then in 8 minutes, the sun would disappear. Then in 8 years, Sirius would disappear. And then in, I don't know, it's like 900 years, Rigel's like 900 light years away. Rigel would disappear, and in 3,000 years, Deneb would disappear. And then in 2 million years, the Andromeda Galaxy would be seen to disappear. So someone asked, how did Edwin Hubble measure Andromeda's distance and speed? Okay, and the answer to that question is he measured the distance using Henrietta Leavitt's Cepheid variables, and he measured the speed using the Doppler effect. It's important to know that when we talk about like the expansion of the universe, of galaxies moving away from us, we do not actually see that galaxy move. Okay, we only see a Doppler effect. All right, we're not seeing the galaxy move, so we don't actually see the universe expand or the galaxies move directly. Okay, if this is a galaxy, put it there. Okay, it takes 100,000 light years for light to cross a galaxy. A galaxy is like 100,000 light years across. So if I set this galaxy in motion that way at the speed of light, okay, go, boom, that's what I would see. Because it would take 100,000 years for it to cross out of its own length. Okay, and well, we don't live 100,000 years. Okay, we'll live 100 years if we're lucky. So in the course of our lifetime, we would only expect to see that galaxy move 1,000th of its overall length, which means hardly at all. And most galaxies don't move at the speed of light or anywhere close. Okay, they move fast, but not that fast. So that is how you get. So you don't see the galaxies moving. We don't see the universe expanding. All right. So Hubble measures the distance using Henrietta Leavitt's distance measuring technique with the Cepheid variables, and he measures the speed of the galaxies using the Doppler effect. Now, another student said, how did they figure out the Doppler effect? And the answer to that question is, I don't know. Sounds like a good thing to Google. I know that you can see the Doppler effect in even the simplest things, like if ducks are paddling really slowly on the lakes, you can see the ripples in front of the duck are compressed together, and the ripples behind the duck are kind of far apart. I should have Googled that when I had that ready for the screen, but I just thought of it now. Okay, so a slow-moving duck, the ripples in the front are compressed, and the ripples behind are far apart. So, you can see the Doppler effect. That's the Doppler effect right there. And then you can hear it if something's moving fast enough. You can hear it in sound if something's moving fast enough. So I'm guessing that the idea might have become more prominent when like higher speed, like you start getting trains and stuff like that move faster. But I think Doppler came before that. So I don't know. I'm not entirely sure how somebody first started working out the Doppler effect. But this isn't rocket science. You can, once you understand, you understand water's a wave, and you can see the Doppler effect with little things moving through water. So once you figure out sound's a wave, you're going to start realizing, the same thing's got to happen for sound. And when you realize light's a wave, you say, same thing's got to happen for light. So I don't know the exact details of it, but I don't think it was something that would have been too complicated to figure out. Another question was, are lighter stars denser? I think by that question is like, are the brighter stars more dense? And that's a complicated question. So it turns out, I said that with stars, you have this star. A star is like a battle between its own gravity, which is trying to crush it in, and this thermonuclear reaction in the center that's making it hot and holding it up. So the brighter stars, in fact, why are they brighter? Because they're putting out more power. Why would they be more powerful? Because their thermonuclear reactions are more powerful. So how could their thermonuclear reactions be more powerful? Well, they must have more gravity, right? Because the thermonuclear reaction of the sun was suddenly cranked up by a factor of 10. You'd expect, well, that'd blow the sun apart. So a star whose thermonuclear reactions are comparable to like 10 suns must have like 10 times as much gravity or more, squeezing it together. So you're going to expect that more powerful stars are going to be larger, more tightly squeezed together object. Now that's not entirely true. Like, there are big, fat, sort of fluffy stars, but it's a great question. Digs into a lot of interesting ideas that you can start thinking about. And it leads to some idea, a variety of ideas like, well, what must stars be like? And I think that to some extent, we would expect that, more powerful stars must somehow be more intense in some way. All right. Another question is, someone asked is, what other galaxies are close by besides the Milky Way? Oh, sorry, we're in the Milky Way. What about besides Andromeda? So let me see if I can get back to that. So there's the Andromeda. That's close by. Where is Andromeda? Oh, he's behind my head. There we are. So there's Andromeda. You can see Andromeda in the sky, just like you can see. And over here is there's the light path there. And there's Andromeda. There. Okay. Andromeda is the only galaxy that you can see easily in the sky from our hemisphere. There is another one that is not that far away in the sky. It's near here in this constellation of Triangle. There it is. Right. There's another galaxy. That one, I've never seen that with my naked eye. I've seen Andromeda but many times, but that one, that's N33. No, I've never seen that with my naked eye, but supposedly you can. And if you go down further to the south, you can see the Large and Small Magellanic Clouds. Those are the clouds that Henrietta Leavitt was assigned to study, in which she made her discovery about the fact that there's these certain types of stars that vary in brightness, and that you can use them to measure distances. All right. So those are two others. There's more. You could Google like local group galaxies and probably find like everything you would want to know about this. I want to say, like there's like 15, 30 or something like that. So the Milky Way's posse, it's got the Andromeda is like the biggest galaxy of this bunch, and then the Milky Way and this guy, the M33, and then there's a smattering of small, little small galaxies. But those are all the galaxies that make up the Milky Way's group, right? And they're the ones that are nearby. They're also all gravitationally tied to the Milky Way. Okay, so these galaxies are all hung together by their own gravity, or sort of orbiting each other. They will probably in the far future kind of merge together. So like Andromeda is not moving away from us. The local group galaxies are not moving away. They're tied together. All the other galaxies in the universe are moving away. But these are sort of a group that is held together. And Andromeda is thought that it will merge with the Milky Way or pass through the Milky Way at some point in the far future. And then, this will gradually change the form of these galaxies as they all kind of blob together over time. Right. All right. Well, I'm keeping it under half an hour. I hope this works so that you can answer your part 2 questions. Nobody particular asked a lot of details about Henrietta Leavitt and how her method works. And so I'm not going to spend a lot of time on it, but I think it's worth mentioning that she discovers that these certain types of stars brighten up quickly and dim down slowly, brighten up quickly and dim down slowly. And then she realized that the ones that are more powerful take a longer time to go through that process, and the ones that are less powerful rise and fall more quickly. So if you look at one of these stars, based on how long it's taken to rise and fall in its brightness, you can figure out how powerful it is. And then based on how bright it looks compared to, what you know about its power, you can figure out how far away it is. Okay, so if you see one that's got a slow cycle, but it looks really dim, well, that's actually a very powerful star. So why would it be dim? Because it must be really far away. And that's how you can, so if you see you can see one of these things in, for example, the Andromeda Galaxy, you see this dim looking little star, and it's going through its cycle really slowly. You think, oh God, that's actually a really powerful star. So how could it possibly look so dim? Because it's so stinking far away. And that is how, Hubble is able to measure the distance to the Andromeda Galaxy, all because of Henrietta Leavitt. Henrietta Leavitt has not, she's like the major breakthrough in modern astronomy, because before Henrietta Leavitt, you don't know how to measure distances in space except for the nearby stars. After Henrietta Leavitt, you know how to measure distances to faraway things, and that's where then you can discover, oh, those things like that there, those aren't forming solar systems, for example, in our own galaxy, which is what was one of the theories on what it was, is that that's a star in formation. No, that's a thing that's so far away, it has to be its own other galaxy. Henrietta Leavitt's only about 100 years ago. Okay, so important NASA scientist Katherine Johnson just died at age 101. When she was born, people didn't know other galaxies existed. So it's thanks to Henrietta Leavitt who develops this method of determining distance we call the standard candle method. Now, since she developed the standard candle with the Cepheid variables, people have discovered other types of standard candles. So there's a certain type of exploding star that they believe these certain types of stars always blow up the same way, always have about the same brightness, so you can use them to measure distances. But she's the first one, and this is the breakthrough that allows us to begin to understand what our galaxy is like and what other galaxies are like. So, all right, we will keep on at this, and now you can. Hopefully, I've provided you with enough information that you can answer at least some of your questions and turn in your Part 2 forms. Thanks. Adios.